Hello there! Welcome to another episode of Bill Nye. Today I'll be teaching you about microstates. The energy of each molecule in the whole system at one instant is called a microstate or a configuration.
Bill Nye the Science Guy. Bill Nye the Science Guy. Bill Nye the Science Guy.
Science rules.
Bill Nye the Science Guy.
Inertia is a property of matter.
Bill Nye the Science Guy.
T minus 7 seconds.
Bill Nye the Science Guy.
A microstate is one of many different accessible arrangements of the molecule's motional energy for a particular material. A macrostate is the thermodynamic state of any system that is exactly characterized by the measurement of the system's properties such as pressure, volume, temperature, and the number of moles of each constituent. Thus, a macrostate does not change over time if its observable properties do not change. Consider two crystals containing 4 atoms each. What will happen when the two crystals are placed in physical contact with each other? Diffusion of atoms will occur. As the particles diffuse with each other, different atoms rearrange across the diffusion border, causing a change in the possible number of configurations. For example, if 0 atoms of A cross the diffusion border, there is one configuration. If 1 or 3 atoms of A cross the diffusion border, there are 16 possible configurations. If 2 atoms of A cross the diffusion border, 36 possible configurations can occur. When equilibrium is reached, the entropy will reach a maximum value. As entropy of a system can be calculated using Boltzmann's equation, the most probable arrangement and equilibrium state can be determined by the arrangement with the most possible configurations.
The number of arrangements in a system of particles is given by the equation for omega. The numerator in the equation, n factorial, accounts for all the possible configurations in the system based on the number of particles available, which in this case is the 3 particles, hence the 3 factorial. The denominator of the equation accounts for the permutations or states that are energetically identical, like in this case states 1 and 2. Since the 2 green particles are the same energetically, the 2 factorial appears. The 1 factorial comes from the red particle's energy state. In this case, the number of possible configurations then becomes 3 as shown in the equation below.
Consider 2 closed systems, A, the blue particles, and B, the red particles. When they are brought into thermal contact, a reaction occurs. The mixing process that follows involves the redistribution of thermal energy among the particles of 2 closed systems when placed in thermal contact. This means that the change in entropy shown in the example is due to the change in thermal entropy. This reaction causes the particles in A and B to rearrange to the most probable state. When the particles in A rearrange to their final positions, this causes a change in the internal energy of the microstate A. In order for the system to remain in equilibrium, the particles in B must also rearrange so that the change in B's internal energy is equal but opposite to the change in A. Therefore, we know that the internal energy of A initial plus that of B initial is equal to the internal energy of A final plus that of B final. Conservation of energy.
So how do you take a microstate and relate it to the macroscopic world that you see around you? Each microstate has particles in different energy levels. We know that each microstate is equally likely, which means that these particles, or electrons, are constantly moving energy levels. So what happens during these moves? Well, Bohr assumed that there are stationary states that exist in atoms, which differs from the classical stable states in that the orbiting electrons are not continuously radiating electromagnetic energy. Instead, Bohr says that these stationary states have definite total energies, hence the concept of energy levels in an atom. Bohr then went on to state that the frequency of the emitted or absorbed radiation is proportional to the difference in energy of the 2 stationary states, meaning that when an electron changes energy levels, energy is absorbed or emitted at a certain frequency. This means that emission of a quantum of light occurs when the atom is in an excited state and decays to a lower energy state. Using his equation, we can find the frequency and therefore wavelength of the emitted photon.